Hi guys, I'm David, and this is a science update for September 23rd, 2021. So the first article that I want to talk about today is from actually the National Science Foundation, and it says biomaterials give the fangs and mandibles of tiny invertebrates an outsized bite. And so this is talking about a paper that we're going to look at soon, but we'll look at this one first. It says insects, arachnids, and worms may have limited muscle power, but they can still pack a punch. These small animals use sharp structures like claws, fangs, stingers, and mandibles to puncture the tough exteriors of larger and more powerful predators and prey. A U.S. National Science Foundation funded study by University of Oregon scientists found metal-rich biomaterials that form the edges and tips of animals' sharp structures. The added sharpness allows these animals to pierce and puncture objects that their size-restricted muscles would otherwise prohibit. So looking at the paper, the scientific paper that little snippet was based on, it's called The Homogeneous Alternative to Biomineralization. Zinc and manganese-rich materials enable sharp organismal tools that reduce force requirements. And this is pretty interesting, so we won't go through everything, but I want to highlight a couple things about this paper that are particularly interesting. So the introduction says there are two distinct classes of inorganic enriched biological materials used in claws, teeth, stings, and other animal tools. The first class, biomineralized tissues, employ mainly calcium, iron, and silicon-based minerals like those in calcified teeth and bones, or in the magnetite-filled teeth of certain mollusks. So that's kind of like the biomineralized thing. You're thinking about teeth and bones that are rich in calcium or iron and things like that. And these biomineralized tissues contain two separate phases. There's usually an organic matrix, which is to say, cells and other things like that. And then there are these mineral inclusions. So these like chunks of mineralized material that are usually bigger than 100 nanometers. And then they're saying that's not the only type of inorganic enriched biological materials used in claws and teeth and things like that. There's a second kind, which they call metal halogen or heavy element biomaterials, and we're going to talk about the differences a little bit in this paper. It says the HEBs, these are the heavy element biomaterials, are distinguished from biomineralized tissue by the apparent lack of separate organic and inorganic phases. So the biomineralized tissue is going to have an organic phase, and then it's going to have chunks of mineralized material in there that's going to give a lot of hardness to the material. And the HEBs, or the heavy element biomaterials, don't really have these separate phases. It's more like the heavy elements are sort of dispersed more evenly throughout the tissue. And basically these two different types of claw material, you could say, have different mechanical properties. So here's a figure that shows some HEB or heavy element biomaterial containing tools. So that you have these little images of the scorpion mouth claws and a spider fang over here to the right, and marginal teeth, scorpion stings, ant mandibles. And what's interesting is they have elemental mapping. You can see that basically you have things like zinc and manganese that are basically spread out throughout the ant mandible, for instance. So what's interesting about this study is that up to this point, only hardness and if in a few cases, a couple of other mechanical properties of these heavy element biomaterials have previously been measured. But what this paper does is it basically looks at these different materials from ants and spiders, scorpions, and things like that, and it put it through a really wide battery of mechanical property tests. So the main finding, so the difference is one better? Is the biomineralized material better, or is the HEB better? But they found that, for instance, a calcified material, a calcified cuticle of a material, which is a biomineralized, was about 3 times harder and stronger than one of these HEBs, but it was much more susceptible to fracture. So in other words, an HEB is usually going to be harder and stiffer than normal tissue, but not nearly as hard or nearly as strong as like a biomineralized material like a tooth or a bone. But it's much less likely to break. and it's much less likely to wear away, so it has better abrasion resistance as well. So overall, I think this is really interesting, and it gives more insights into how it is that a lot of insects are able to, I think as the NSF article put it, like bite above their weight class. Has a lot to do with the fact that the biomaterials of its mandibles are really, really sophisticated. So for the next article that I want to talk about today, it's from phys.org, and it says scientists still don't know how far melting in Antarctica will go or the sea level rise it will unleash. So on the left is the sea level in meters. And most likely, under most scenarios, they're saying that we'll probably have less than a meter rise in sea level by 2100, but there are some scenarios where you could see maybe 1.5. It says the Antarctic ice sheet is the largest mass of ice in the world, holding around 60% of the world's freshwater. If it all melted, global average sea levels would rise by 58 meters, but scientists are grappling with exactly how global warming will affect this great ice sheet. So obviously 58 meters is a lot more than the 2 meters that we're talking about here, so I'm curious to see if they'll reflect on that. Projected sea level rise will have widespread effects in Australia and around the world, but current projections of ice sheet melt are so wide that developing ways for societies to adapt will be incredibly expensive and difficult. And they're basically saying that it's the uncertainty surrounding this question that poses a big challenge. There's a couple different mechanisms. One that makes it very difficult to figure out are the mechanisms surrounding what's called basal melt, which is melt from below the ice sheets, which is thought to be primarily due to interactions with the ocean, interacting basically underneath the ice sheets. But this is challenging because in terms of prediction and interpretation, because gathering the data for what's going on underneath the ice shelves is just fundamentally difficult. So they're talking about a study where they were looking at basal ice melt projections, and they admit that the model is really, really uncertain, but that doesn't mean that we shouldn't pay attention to it. To some extent, we should just take it with a grain of salt. But the study also outlines a pessimistic but still plausible basal melt scenario for Antarctica, in which sea levels could be 5 times higher than the main scenarios. So instead of, maybe 1 meter by 2100, we'd be looking at 5 meters, which is really going to be a big difference in terms of the impact on human society. So reading this article made me think, just in general, well, what really does happen if you have a certain rise in sea level? So I found this sea level simulation, and this gives us a map of different regions. We can look at it, and it shows the current sea level, basically. That's in blue. You can see the contours of Florida, for instance, and it gives you the ability to raise the sea level up to 10 feet. So that gives us about a 3-meter rise, about 3 meters. So that's more than the 2100 projection, most of them, but obviously it's very far shy of the 58 meters. That would be the maximum, but still it's interesting. So if we rise the sea level up to 10 feet, you can see that there are quite a number of cities which essentially became inundated, including Miami. Norfolk, Virginia doesn't look like it's in good shape. Dover, Delaware. Boston is probably underwater. Obviously, a lot of Louisiana and Mississippi are going to be in trouble. So if we take it back down and then look at it again, just to see the contrast. So if we look, for instance, at Florida in particular, maybe I'll zoom in to make it easier to see what's going on. So looking at Florida, it's pretty, we're at no sea level rise, and then we'll bring it up to 10 feet. You can see that that's going to be a lot of trouble for people and for animals. So that's interesting, but it still doesn't give us a sense of what would happen if Antarctica completely melted. And I wonder if it's even, I was thinking, like, is it even reasonable to expect that all of Antarctica could melt? And so that got me thinking of, well, has Antarctica ever been completely melted in the past? Was there a time when Antarctica was not melted? So I did a little bit of research, and it turns out that Antarctica was not always at the South Pole, so there was a time where parts of Antarctica were actually near the equator. But because of plate tectonics over time, Antarctica has moved very dramatically. However, there was quite a while that Antarctica was at the South Pole, but was not frozen over yet. So I found this website. It says when Antarctica went into the deep freeze. It says Antarctica hasn't always been covered with ice. The continent lay over the South Pole without freezing for almost 100 million years. Then about 34 million years ago, a dramatic shift in climate happened at the boundary between the Eocene and the Oligocene epochs. The warm greenhouse climate, stable since the extinction of the dinosaurs, became dramatically colder, creating an ice house at the poles that has continued to the present day. So that's really interesting. There was quite a while where Antarctica was at the South Pole and was an uncovered continent. So the fact that it had happened before means that it could probably happen again. So it's probably not unreasonable to predict, maybe not in the next 50 years or something, but in the next couple hundred years, the idea that Antarctica could completely melt and we would have that 58-meter rise in sea levels is not totally absurd. Thanks again for watching. This has been another science update. I hope you will join me again in the future soon.